We're starting a new section on weather and climate. This is often new material for students. I don't know what it is, but for some reason this information is often skipped in our previous classes. Because it can be difficult, what we're going to do is start off with these easy baby steps and work into these more difficult processes over the coming weeks. Today's mini lecture is a series of introductory concepts and processes that should feel fairly easy as we begin our introduction to Earth's atmosphere. Our atmosphere contains 78% nitrogen, 21% oxygen, 0.04% carbon dioxide. That number is significant to us. We know that number continues to rise as we add more greenhouse gases to our atmosphere, and this is what is creating global climate change. And finally, we have just about 1% of all other gases, which consist of mostly argon. Next, we're going to draw and label the vertical structure of the atmosphere. We'll begin down on Earth's surface and shoot straight up into the sky like a rocket until we get into outer space. Let's draw this out together. On your own sheet of paper, draw an axis like you see drawn here, with the bottom blue line representing the surface of Earth, and then we're going to shoot straight up into the sky to show these layers that go up into our atmosphere. We live in the troposphere, and as we continue up into the troposphere, we hit the transition zone called the tropopause. The next layer is the stratosphere. From there, we hit another transition zone called the stratopause. The next layer is the mesosphere. Then, yes, you guessed it, we hit that transition zone called the mesopause. The next layer is called the thermosphere. After the thermosphere, there is not one of those transition zones. This just takes us into the exosphere, which is what you and I would consider space, outer space. When measured from Earth's surface, the troposphere extends up about 11 miles. The stratosphere extends up about 30 miles. The mesosphere extends up about 50 miles. And the thermosphere extends up about 125 miles. You and I typically think of elevation or altitude in feet, so let's understand that the troposphere extends up to 58,000 feet, or 11 miles. We live in the troposphere. Are any of us ever going to get out of the troposphere? Well, you're looking at the tallest peak in the whole world. It's in the Himalayas, and this is Mount Everest. At 29,035 feet, Mount Everest would peak at about halfway into the troposphere. Mount Whitney, which is the tallest peak in the contiguous U.S., it's found in California, peaks at 14,494 feet. So we should draw Mount Whitney only about halfway up Mount Everest. What about commercial airlines? How high do they typically fly? They fly at about 35,000 feet. As you can see, the bulk of us are going to spend our entire lives living in the troposphere. Unless you're an astronaut or pay one of those big buck bucks rocket rides out into outer space someday, you and I are going to spend our entire lives in the troposphere. In fact, the bulk of our weather is found in the troposphere. We have some big cumulonimbus storm clouds that peak up into the stratosphere, but the bulk of our weather is found in the troposphere as well. On this much more attractive diagram, you can again see the various layers from the troposphere to the stratosphere to the mesosphere to the thermosphere, and again on into the exosphere. But also notice the temperature that is displayed along the x-axis and that altitude is displayed along the y-axis. Without me even showing you this diagram, if I asked you that as we go up in altitude, does it get colder or warmer, you would know that in the troposphere, it gets colder. And you can see that in this diagram, that in the troposphere, it gets progressively colder. In the stratosphere, it gets progressively warmer due to the ozone layer. In the mesosphere, it gets progressively colder, and in the thermosphere, it gets progressively warmer. As a geographer, which of these layers are we going to be the most interested in? As a geographer, we're most interested in the troposphere. Why? Because we always come back to that human-Earth relationship. So with regard to temperature, we know that as we go up in the troposphere, it gets progressively colder. And you already know this. If I said, hey guys, let's go up to Big Bear Mountains today, you would know, well, I better at least bring a sweatshirt, if not a jacket, because it will be colder up in the mountains than it is down here closer to sea level. But why is it colder up in the mountains? Well, it has to do with air pressure. What is air pressure? Air pressure is the impact and collision of billions of molecules. The impact and collision of billions of molecules. It is the weight of air molecules pressing down on Earth. The bottle on the left is found at about 14,000 feet, and the bottle on the right is found at sea level. At sea level, the sheer weight of all the air above it makes that air more compressed. At sea level, we have higher air pressure, and as we go up in elevation, air pressure gets progressively lower. At higher elevations, the air pressure is lower because there is less air on top of those air molecules. To help you remember this, think about a football game. The guy that gets tackled and is on the bottom, is he under more pressure or less pressure? He has more pressure because of the sheer weight of all the football players piled on top. So what is the relationship between air pressure and temperature? Here's one of these 5-star rules that you need to remember. And the rule is that as gas is compressed, its temperature increases. I keep telling you guys stuff you already know. You know that when gas is compressed, its temperature increases. You've experienced that when you pump up the tire on your bike. What happens to the tire pump? It gets warmer, right? Why? Because the air inside the tire pump is being compressed. Or you know that compressed air can you use to clean your keyboard? What happens once you spray it? The can gets extremely cold. Why? Because the air is less compressed inside the can once you spray it. So with regard to temperature, altitude, and pressure, At the bottom of the mountain, we have higher pressure. The air is more compressed, which is going to make it warmer at the bottom of the mountain. As you go up in elevation, the air pressure is lower. The air is less compressed, which makes it colder in higher elevations. Let's move on to another topic as we are understanding these basic concepts and processes to better understand weather and climate. Let's make sure that we are clear about the similarities in temperature between latitude and altitude. At the lower latitudes, closer to the equator, this is an area that is warmer. And as we get further away from the equator, it gets progressively colder in both hemispheres. Eventually, we get to something called tree line, where trees don't grow anymore. And we also eventually find glaciers that are still melting since the last ice age. In the same way that we say that the lower latitudes are warmer, and as we go into the higher latitudes, it gets colder, we can say the same thing about altitude. At the bottom of the mountain, in the lower elevations, it is warmer, and as we go up in altitude or up into the mountains in elevation, it gets progressively colder. And yes, we hit an area called tree line where trees don't grow anymore. And we also eventually will find glaciers in those higher elevations. So there are similarities between latitude and altitude with regard to temperature. Finally, let's look at the differences between land and water. That leads us to another one of those 5-star rules. And the rule is that land heats faster and cools faster than water. Land heats and cools faster than water. So we can also say that water heats and cools more slowly than land. But you already know this. I keep telling you things that you already know. Look at this example. Let's say we're all going to go to the beach. It's July. We get there at about 2 o'clock in the afternoon. We park right next to the sand, but we need to get to our favorite spot that is about a football field away. It's 100 yards away from our car, and we have to walk along the sand in July at 3 o'clock in the afternoon. And every single one of us forgot our flip-flops. How are our footsie-wootsies going to feel after that 100-yard walk on the hot sand? Our feet are going to be on fire. Our footsie-wootsies are going to be hot tamales. We will have blisters, and we will be crying because the sand is so hot. Now, at the same exact time of the day, go put your feet in the water. How does the water feel? Nice and cool. So wait a minute. The land and the water are right next to each other. They've received the same amount of insolation, the same amount of incoming solar radiation since the time the sun went up, and yet the sand is hot tamales, we're crying, and the water is nice and cool. How does that happen? Why? Because land heats faster than water. Water has a high specific heat. What that means is it takes more heat energy to heat up water than it does to heat up land. Once again, I'm telling you something you already know. Let's look at an example. If you're going to heat up some water for coffee or tea in the morning, how long do you put it in your microwave? Some of you might put it in for 2 minutes, maybe 2.5. Some of you might even put it in for 3 minutes, depending on the speed of your microwave. I would have no concern putting my water in the microwave, setting the timer for 2.5 minutes, leaving the room, going in and brushing my teeth, and coming back, finding my water nicely heated. But Would I do that with a Cinnabon? You know, those heavenly treats that you might buy while you're at the mall? Let's say that for breakfast, we have a Cinnabon and we're going to reheat it in the microwave. How long are you going to put it in there for? You're cautious, right? Nobody's going to put it in there for 2 minutes, 2.5 minutes, 3 minutes. You might ease into 20 seconds, test it, and make sure it's safe before you put it in any longer. You want to be cautious with this thing. Why? Why do you need to be so cautious with the Cinnabon? Because Cinnabons heat faster than water. Water heats more slowly than your Cinnabon. Now, place your heated Cinnabon and your heated coffee on your desk, which is going to cool down more quickly. The Cinnabon's going to cool down more quickly, right? Why? Because in the same way that land heats and cools faster than water, Cinnabons also heat and cool faster than your coffee. If we stayed at the beach that same day where during the day at 3 o'clock in the afternoon, the sand was so hot it was burning our feet, if we stayed all day into the evening, what does the sand feel like at about 10 o'clock at night? The sand feels much cooler, right? It went from super duper hot at 3 o'clock in the afternoon, and at 10 o'clock in the evening, the land is cold. Why? Because land heats and cools fast. And what about water? That same time at 10 o'clock at night, what's the temperature of the water? Well, the water is actually the same temperature as it was during the day. Water heats and cools slowly. Over the course of the day, the water temperature is basically going to be the same in the ocean. And over the course of the year, it's not even going to change that much because water heats and cools more slowly than land. How do these land and water differences affect weather and climate? Let's look at that now. Places that are closer to coast, they're going to have a more moderate temperature. There won't be a big range in temperature on a daily level as well as annually over the course of the year. In comparisons, places that are surrounded by land experience something called continentality. And these places will have big extremes daily and over the course of a year with regard to temperature. It can be freezing with loads of snow in the winter, and it can be really hot and warm in the summer. Places that are closer to the beach, even our local beaches, are a good example of in the winter it's not too cold, and in the summer it's not too hot. Proximity to large bodies of water moderates temperatures over the course of a day as well as over a year. These basic weather and climate concepts will be added to some more difficult processes going forward.